conductor in terms of resistivity, current carrying density, and specific gravity S. So over here, you can see that the units of resistivity are in micro ohm centimeter, which are not the SI units. Similarly, for density, it is ampere per millimeter square. So for deriving, what we can do is we can take resistivity and convert it into micro ohm millimeter. So this will become 10 times rho. Then the loss is I square R, substituting R as rho L by A and I as sigma times A, where sigma is the current density, A is the area. We get this, and simplifying it, we get sigma square 10 rho AL. So L and A we have taken in meter, rho is in micro ohm centimeter, and multiplied by 10 gives in millimeter, and sigma is in ampere per millimeter square. So this is the loss. Now for loss per kg, we'll divide by the weight of the conductor, that is density times volume, and simplifying it, we get the answer. So I hope it is clear to everyone. Anyone has any doubts, please ask. Okay. So next question. A source of EMF E and internal resistance R supplies current to a heating coil. Calculate the resistance R of the coil so that heating takes place most rapidly. And second part is 3 by 4 of the total energy developed by the generator is absorbed by water. So for first part, uh, first let us calculate the loss in resistance R, which is I square times R, where I is E by capital R plus small r. Now for max heat supply, we want to find R, so we'll differentiate it with respect to R, capital R, and we equate it to 0, and we get that capital R should be equal to small r for maximum heat. This is also the maximum heat transfer theorem that I think will be covered in the coming week or so. Now for B part, they said that 3 by 4 of the total energy developed by the generator is absorbed by the water. So energy developed by the generator is V, that is E times I, that is E by capital R by small r, and heat supplied is 3 by 4 of the total energy developed, which we want, and equating the heat supplied that we calculated in the last in the previous part equal to 3 by 4 of total energy developed, we get capital R is equal to 3 times small r. Third question. A coil of inductance L equal to 0.25 Henry and negligible resistance is connected to a source of supply represented by V equal to 40 volts. If the voltage is applied at t equal to 0 seconds and switched off at t equal to 5 seconds, find the maximum value. So we have an inductance whose value is 0.25 Henry, voltage is 40 volts. So the voltage is applied from t equal to 0 to 5 seconds. It is given in the question. Now we have studied that the relation between the current and voltage for an inductor is L di by dt equal to V. Integrating with respect to I and with respect to t, by substituting the values of L, we get that I at any particular time t is 8t square. Initially the current is 0, and yeah, that's it. So the maximum value is achieved at 5 seconds. This is a parabola, so it is increasing at from t greater than 0. So at 5 seconds the maximum current value is 200 ampere. Now the second part was that we wanted to calculate the RMS value of the current using the formula of RMS, that is integration of the square of current with respect to t divided by the total time. The root of this is the RMS value. So substituting the integrating and then substituting the value of final t as 5 seconds, we get that the RMS value after all these calculations is 89.443 amperes. Then the energy stored during this period T equal, so the energy stored for an inductor is half into Li square. At t equal to 5 seconds, we calculate the current using this formula, which gives that the current is 8 into 25, that is 8 into 25. So total energy stored at t equal to 5 seconds is half L I square, that is 5000 joules. Now fourth question. Anyone has any doubts? Okay, I can see your message. You're not able to see the screen? Hello? Can someone please reply?
Yeah, the screen is visible.
Okay, fine. Okay, now fourth question. Two coils are connected in parallel and a voltage of 200 volt is applied to the terminals. The total current taken is 25 ampere and the power dissipated in one of the coils is 1500 watts. What is the resistance of each coil? So like this is the setup. Two coils are in parallel. The total current going through both the coils is 25 ampere and they are connected across a 200 volt source. So power through R1 is given to be 1500 watts. Now power is V square by R. So 200 square by R1 is equal to 1500, which gives R1 as 26.67 ohm. And the total current is 25 ampere. So equating the total current equal to the current in the R1 and R2 branches, we get that 200 by R1 plus 200 by R2 is equal to 25. Substituting R1, we get R2 as 11.48 ohms. Fifth question. A resistance R is connected in series with a parallel circuit comprising of two resistances of 12 and 8 ohms respectively. The total power dissipated in the circuit is 70 watts when the applied voltage is 20 volts. Calculate R. So first we can calculate the effective R of this entire setup, in which these two are in parallel and in series with R. So we get that the R effective is R plus 4.8 ohms. Now the total power dissipated in this circuit is 70. So V square by R effective is equal to 70. Substituting V, we get R effective as 5.714 ohms. So then using R plus 4.8 ohms equal to 5.714, we get R as 0.914 ohms. Now sixth question. A wire is bent into a plane square of 12 inches side and a current of 250 ampere is circulated round it. What is the magnetic flux density at the center of the square? So this is the setup, and A is the length of the side of the square. Now, like I think this we have studied in JEE, that the magnetic field at a distance from one particular conductor is mu naught I by 4 pi a sine theta 1 plus sine theta 2. where theta 1 and theta 2 are the angles that the ends of the conductor make with the point. So adding the magnetic field due to all the four conductors, and they all will add up because using the right hand rule we can see that the direction of magnetic field due to all the conductors is the same. So we get that the net magnetic field at the center point is 2 root 2 mu naught I by pi a. Directly substituting the values, we get the magnetic field at the center. So this question is just a recap of what we did in JEE. Seventh question. Yeah. So 2 voltmeters A and B have resistances 5000 ohm and 15,000 ohm respectively. And they are joined in series across 240 volts. What is the reading of each voltmeter? So this is the setup, 2 voltmeters across a 240 volt source. They are both in series, so we calculate the total current that is flowing through these voltmeters. That is 240 by 2 into 10 raised power 4. And then the voltage across 1 voltmeter is I into the resistance, that is 5000 ohm. So we get 60 volts. Similarly, voltage across 15,000 ohm voltmeter is 180 volts, and that's the answer. Yeah. So, eighth question. An air condenser consisting of two parallel square plates of side 50 centimeter is charged to a potential difference of 250 volts when the plates are 1 millimeter apart. Find the work done in separating the plates from 1 millimeter to 3 millimeter, and we assume perfect insulation. So when we increase the separation, charge will remain constant. So initially we can calculate the charge using the formula Q is equal to CV. We know that V is equal to 250 volts, and we can calculate C using this formula, where E is the area of the square plate and D is the distance between the plates. So we get that the charge is 553.386 nanocoulomb. Now we calculate the final capacitance, because on increasing the distance the capacitance value will change, and the total work done will be the change in energy. So substituting, so the final DF was 3 millimeter, area was same, and this constant is the same. Now energy change is equal to half into Q square by C, where C changes from CF to CI, and substituting the values, you can substitute it and check that it is 138.34 microjoules, and erg is another unit for energy, and the conversion between joules and ergs is this. So now we'll go to the ninth question. A resistance of 10 ohm is connected in series with two resistances, each of 15 ohm, arranged in parallel. What resistance must be shunted across the parallel combination so that the total current taken shall be 1.5 ampere and 20 volts? So, yeah. So it is given that for getting 1.5 amperes with 20 volts, the resistance should be V by R, that is 13.33 ohms. This is the resistance that we want. And let us assume that the resistance that we are shunting across is X ohm. So the effective resistance of the entire setup will be 10, which is in series with the added resistance and the 215 ohm resistances, and all these three are in parallel. So we equate it to 13.33 ohms, and we solve this equation to get that X is 6 ohm. Question. A constant voltage E is applied to n groups of rheostats in series, where each group has m identical rheostats in parallel. So there are total n into m rheostats. One rheostat burns out in one group. Find the percentage increase in current in each rheostat of the faulty group. So when one of the rheostat burns out in one group, that parallel branch becomes, the resistance of that parallel branch becomes infinity. So that no current flows in that branch. So given n groups of rheostats in series, with each group having m parallel rheostats, we'll assume that the resistance of one rheostat is R. So before the rheostat burns out, the voltage across each rheostat group is E by N because n groups are in series, and current across each rheostat will be the voltage across it divided by R. So V by R. After burning of the rheostat, the total resistance becomes so n by 1, n minus 1 combinations have all the rheostats intact. So these are in so all m are intact. So R by M is the effective resistance in parallel, and there are n minus 1 such in series. So R by M into n minus 1 plus this is the branch in which one rheostat has burnt out. So m minus 1 rheostats are in parallel. And then this is in series with rest of the other combinations. So this is the total resistance. Then current is E by this total resistance. And so this is the current that is flowing in series. So for one rheostat, the current in the faulty group will be divided by m minus 1 of this total current. So percentage increase can be calculated by y minus x by x into 100, where this is x, this is y. Eleventh question. A cell supplies 48.8 milliamperes to a 25 ohm load and 25.9, this is milliamperes, I think there is an error, to a 50 kilo ohm load. Determine its EMF and internal resistance. Assume both to be constant and find the terminal voltage of the cell when connected to a 40 ohm load. Okay, so for the first part, so this is the EMF of the cell and this is the internal resistance of the cell. So we simply equate the voltages. So E minus 48.8, that is current, into internal resistance is equal to the voltage across the 25 ohm resistor connected across the cell. Similarly for the other case, and solving these two, we get R equal to 3.275 and E equal to 1.38 volt. Now for the second part, when we connect a 40 ohm load, terminal voltage is E minus the current into internal resistance, and the current will be E by the total resistance in the circuit, that is 40 plus internal resistance. So substituting the values of E and R, we get terminal voltage as 1.275 volt. 12th question. A 20 volt battery with an internal resistance of 5 ohm is connected to a resistor of X ohms. If an additional 6 ohm resistor is connected across the battery, find the value of X so that the external power supplied by the battery remains same. Fine. So when the 6 ohm resistor was not connected, the external power supplied by the battery will be the power delivered to the X ohm resistor. So that will be the current in this resistor I square R, where I is the current in this resistor and R is X. So this is the external power before adding the 6 ohm resistor. After adding the 6 ohm resistor in series with X, the external power will become the current in these two resistors, square of that into the sum of the resistors. So equating the external powers in both the cases as asked in the question, we can solve X and we get that X is 2.83 ohms. Two 12-volt batteries, question 13. Two 12-volt batteries with internal resistance of 0.2 ohms and 0.25 ohm respectively are joined in parallel and a resistor of 1 ohm is placed across the terminals. Find the current supplied by each battery. So all these questions are very similar, but it will be good if you practice them on your own. Two batteries of 12 volt with internal resistance 0.2 and 0.25 ohms are connected in parallel, and they are connected, and a 1 ohm resistor is connected across them. So we are taking the current in this branch as I1, this branch as I2. So the current in this branch will be the sum of both these I1 plus I2. So we can find I1 and I2 by applying KVL, Kirchhoff's voltage law. Everyone knows what is Kirchhoff's voltage law, right?
Yes, ma'am.
Okay, fine. Yeah, so applying Kirchhoff's voltage law once in this loop and once in this loop, we can find the equation. So 12 minus 0.25 I2 is equal to I1 plus I2, voltage across this. And then in this bigger loop, 12 minus 0.2 I1 is equal to I1 plus I2. Solving 1 and 2, we get that I1 is equal to 6 amperes and I2 is equal to 4.8 amperes. Question 14. Two heaters A and B are in parallel across supply voltage V. Heater A produces 500 kilocalories in 20 minutes and B produces 1000 kilocalories in 10 minutes. The resistance of A is 10 ohm. What is the resistance of B? And the second part is, if the same heaters are connected in series across the voltage, how much heat will be produced in 5 minutes? So like in basically in these questions we are trying to change the units which are not the SI units, and for cases like kilocalories and all, it is good that you recap your previous knowledge of the conversion between the SI units and like kilocalories, so it will be helpful. So A produces 500 kilocalories in 20 minutes and B produces 1000 kilocalories in 10 minutes, and we are given that the value of A is 10 ohm and we need to find V. So like for A, the I square RT is the energy which is equal to 500 kilocalories. So first we'll convert these kilocalories to joules. So 1 kilocalorie is 4184 joules. Now I square R is substituted as V square by R into 20 into 60. So we are converting minutes into seconds, is equal to the energy in SI units, that is joules. So we get V is equal to 132.035. Now using this V for B, we get that V square by RB into the time in seconds is equal to the energy, the heat in B, that is in joules, that is 1000 into 4184, and we can find what is RB. Then we come to the second part of the question, that A and B are connected in series and V is the same that we calculated in previous part. So it is 132.035. I hope my pace is okay. Everyone is able to understand, right? Because no one is speaking, so I am a bit skeptical. Everyone is able to understand, right?
Yes, ma'am.
Okay, fine. So heat produced in 5 minutes is I square times total R into time in seconds. So we substitute I square R as V square by RA plus RB into time, and V is 132.035. RA and RB we have calculated in the previous part, and time is 5 into 60 seconds, which gives the total heat generated as 100 kcal. Like we have to convert from joules to kilocalories, okay, for the final answer. Question 15. Find the equation of the voltage to be applied to a 50 microfarad condenser. Condenser is a capacitor. Initially uncharged to produce a steady current of 10 milliampere. If charging ceases after 10 seconds, calculate the condenser voltage, charge and stored energy. Okay. So we know this equation of for a capacitor that C dV by dt is equal to I, and I can be written as dq by dt. So Q is the charge. So we are given the value of capacitor as 50 microfarad, I as 10 milliampere. So for the first part, we want to calculate the voltage. So using C dV by dt equal to I, so we know that the I is at a steady value of 10 milliampere and the charging time was 10 seconds. So we integrate this equation with respect to V and T. So from 0 to V. So I have directly substituted 10 seconds over here, but a more general approach would be that write T over here and then later substitute whatever time is given. So 50 microfarad. So this will be V times 50. I've converted it into farad is equal to I into 10 raised to minus 3 is for milliampere into the limits of integration, that is 10 minus 0. So we get V as 2000 volts. Next we have to calculate the charge. Now for calculating the charge, we will use the other equation, that is I is equal to dq by dt. Again we know that I is 10 milliampere. So we integrate it by taking dt to the other side, and we can integrate it with respect to t and substitute 10 later. So, and the limits of integration over here, since it was given in the question that capacitor was uncharged, we have initial charge is taken as 0 and the final is taken as q. So we integrate and we find that q is 0.1 coulombs. For stored energy, the formula for a capacitor's energy is half CV square. Substituting C and V, we get it that the stored energy is 100 joules. Question 16. The voltage shown in figure 1 is applied to a 2.5 microfarad capacitor and a 0.5 Henry inductor with no initial current. Plot to scale the graphs of IC and IL. Okay, so this is the graph for voltage versus time for the capacitor. Now we'll use these two equations, that current in a capacitor is equal to C times dVc by dt, and for an inductor the voltage across the inductor is L di by dt. So firstly for the capacitor we calculate dVc by dt from this plot. So we'll divide it into two parts till 4 milliseconds and after 4 milliseconds. So dVc by dt till 4 milliseconds is the slope of this line, which is 20 plus 20, 40 by 4 milliseconds. So that is 10 raised per 4. And similarly, we will calculate the slope for this line from 4 to 5. So for the interval between 0 to 4, it is the dVc by dt is 10 raised per 4, and between 4 to 5 milliseconds it is minus 2 10 raised per 4. So now we can substitute dVc by dt in this equation and find the value of IC for these two time intervals, and we can directly plot it. So from 0 to 4 the current is 25 milliampere, and from 4 to 5 it is minus 50 milliampere. Now for second part we will calculate it for an inductor. For an inductor we know that VL is equal to L DIL by dt. Taking dt to the other side and integrating from 0 to t, we find IL. So first let us calculate VL, and then we'll substitute VL over here and get IL. So VL. Now for VL, we'll have to find the equations of these two lines. That will be VL. So we have already calculated the slopes of these two lines, and looking at the intercept we can find the equation of the straight line. So these are the two equations of the lines, and we integrated from 0 to t uh, by substituting it over here to get IL, and the final answer will be uh, this, and we can just plot it on the graph over here. So yeah, I think the questions are over. Anyone has any doubt, they can ask, and they can, like, if they're solving it simultaneously, I'm around here for some time, you can ask me any questions while you are solving as well. So basically this was just an introductory tute. From next time onwards we will, like, most of you might find this similar to what you did in JEE. From next time onwards, when network theorem and everything will come, we'll have some new things to discuss. And I wanted to ask, is my speed okay, or shall I slow it down?
Now I guess it's fine.
Okay, great.
I had a doubt regarding the quizzes.
Yeah.
Means if these type of questions come, then how much are we expected to explain in the box that the theory regarding this? The final answer we have to write, but the explanation how much we have to do.
Okay, so generally in quizzes, you don't have to explain a lot. You can show the formula, and you can just show the steps that you have done. You don't have to talk much about the theory, and like these kind of questions in general won't come. So the questions will be a bit more, like, it would be similar to what you have studied in class, but the questions will come from what you are covering this week and next week mainly, and after that. So you can just show the steps that you are doing. That would be enough.
Okay, ma'am.
Like when I was solving for I1 and I2, I wrote, right, that applying KVL, I came at this equation, applying for this loop, so that those steps are enough.
Okay, ma'am. Thanks.
So what is being covered in class this week? The network theorem, right?
Ma'am, we don't exactly know because like the syllabus has not been exactly shared. The last class what we finished on was basically we had discussed capacitance and inductance, like the basic formulas, and we were like just coming like to constructing circuits. I mean, like basic symbols were done. Ki these are the symbols for this and this. And then we were starting to construct circuits. So I think that's our status currently. What comes after that, I don't know.
Okay. So if no one has any doubts, we can uh, stop the tutorial for this week, and hopefully we'll have some more interesting questions to solve next time. Okay, so I don't think anyone has any doubts. But please make sure that you solve the tutorial and during the weekend and then come for it on Monday. It would be much more useful for you. So, okay, thank you.